Hey, welcome back to another exciting day of a couple examples. So on this, we're going over when something gets launched horizontally. So instead of something being dropped, we're talking about a horizontal projectile. So there's a couple key things that we always want to talk about. So let's just kind of, same process of everything that we've been doing. Let's just see how it goes. All right, first example problem. A ball is thrown horizontally, so that's important right there, off the roof of a school. It's thrown with an initial speed of 20 meters per second, and the building is 11 meters tall. All right, so first problem, how long is the ball in the air? So right away we have some numbers and stuff given to us. We want to fill in our little table of values. Okay, so when something is launched horizontally, right, that means that all of its initial velocity right there is horizontal. So that means that if something is going 20 meters per second horizontally, everything is in the x direction and there's nothing there in the y. If you take a look, this is a vector because it's pointing somewhere. There's nothing pointing up or down yet. There's no y velocity. So all of the initial velocity is in the x direction. Okay, there is nothing in the y direction. And that is a indicator, or like that happens anytime something is a horizontal projectile, there's no y velocity. Okay, and let's see, what else do we know? We know the building is 11 meters tall, so by the time it hits the ground, it will have gone down 11 meters in the y direction. Okay, and we don't know what the final velocities are right there. What we do know is the acceleration. Remember, projectiles, there's always 0 acceleration in the x direction and then -10 in the y direction. All right, and we don't know time yet or anything like that, so that's all we know so far. Okay, and part A says, how long is the ball in the air? So we are trying to find time for this first part. Okay, so if I take a look at our projectile equations, or our kinematic equations, and take a look at all the info I have, the only one that I have enough info to use is in this y direction. So I'm only going to use y numbers to figure out this next part. All right, so the equation that has all those variables in it that I need is change in y position is equal to initial y velocity plus 1/2 at squared. Right? And a couple things happen. The initial velocity in the y right here is 0. So that goes away. And then we can rewrite it real quick. And now it just becomes plug and chug. Do a little math, solve for t. Okay, I would end up with t is equal to the square root of 2 times the displacement over a. Okay, and then when we plug in all of our numbers, that would come out to about 1.5 seconds. So 1.5 seconds can now go in both columns. Remember, time is the only thing that gets shared in the x and y direction. Okay, so now I got a little bit more in my table. So part B, well, how far from the building does the ball land? So imagine like if this is our building, right? Ball started going this way at 20 meters per second, and it goes and lands down on the ground. Okay, that distance right there, that's the how far part, right? So that how far is always talking about displacement in the x direction. So that's the entire goal with this one. Find the displacement in the x direction. So now, because I'm doing x direction, I can only use numbers from the x column. Okay. So we can use the same equation. It has all the same stuff that I'm trying to solve for. Change in x position. Okay, remember in the x direction there's no acceleration. It's constant velocity to represent that motion. So if there's no acceleration, this whole last term goes away. We can rewrite that real quick, make it a little nicer. V naught times time That's all it is. The initial velocity was 20 meters per second in the x direction. We just found the time was 1.5 seconds, which gives us that it went 30 meters. Okay, and part C, what are the x and y components of the ball's velocity just before it strikes the ground? Well, when it flies through the air, remember it starts with 20 meters per second, and then as it's fallen through the air, remember that 20 stays the same the whole time. There's no acceleration. What happens is it's going to start falling a little bit faster and a little bit faster, right? So what it's asking for is, we know the x component. The x component right away is 20 meters per second. That never changes for a projectile. What we need to do is figure out what the y component is. What is this downward arrow and how big is it? So we're looking for the y velocity when it reaches the ground. Okay. Well, if I want to find a final velocity, probably the easiest way for us to go about that is our equation right there. Okay. We know the acceleration in the y direction. We know the time. We know the initial velocity. Now it's just seeing how it goes. Okay. It is going speeding up down at -10 meters per second every second, and it was falling for 1.5 seconds. So the final y velocity would be -15 meters per second. So right there is your two components, your x component and your y component. All right. For the next example, it's kind of all this stuff wrapped up together, because they're not, this was giving you like pieces of the puzzle, how long is it in the air? How far does it go? Blah, blah, blah. The next example is asking you just the last part. How far does it go? So you got to fill in the gaps between. So a cannon is shot from the top of a 100-meter tall castle. So right away that tells me the ball's going to fall 100 meters. So -100 for the y displacement. The cannon is shot horizontally, right? Horizontally tells me there is no initial y velocity. And it has an initial speed of 150. All right. And the question is, how far will the cannon shoot? Our ultimate goal is figure out what is this x displacement? How far? Okay. We got to fill in all the gaps between that. So I know how fast it's going. If I know how fast it's going and how long it's in the air, I can figure out how far it's going to go. Okay, so the in-between step is going to be us trying to figure out what the time is. So there's some other things that I can know. I know a projectile always has 0 acceleration in the x and -10 acceleration in the y. Okay, so I need to figure out how long it's in the air. So I'm going to use the y values to figure out all of my time stuff. So same equation we used earlier. Scroll that up a little bit. There we go. V naught times time plus 1/2 at squared. This is a horizontally launched projectile, so there's no initial y velocity. So there's no initial velocity in the y direction. So that term goes away. All right. Solve for t. And when we plug in all of the numbers that we have, we come out to approximately 4.5 seconds in the air. Okay, so that gives us 4.5 in the y and 4.5 seconds in the x. Remember, the only things that get shared in those two columns. Now, if you take a look at the x, I have enough info to use one of my equations to figure out how far it's going to go. And it actually ends up being same equation. Okay, so for the x direction, the how far part now, we go change in the x position is equal to initial velocity times time. We start with the general equation, and then we kind of go, oh yeah, it's a projectile. There's no acceleration, so this whole term goes away. And initial velocity times time. Now we can plug in all of our stuff. Initial velocity was 150 meters per second. It was in the air for 4.5 seconds. So 675 meters. That's how far away the cannonball is going to land on the ground. Okay. So some kind of like, relatively simple math, and then it's just kind of figuring out how to make all the pieces fit together. Normally, we're going to use the y direction to find time, just because we kind of know more about the y direction usually. And then once we know time, that gets shared between both x and y, so it's easy for us to go back and forth. Okay, but yeah. All right, I will see you guys in class. Looking forward to seeing you guys again, and see you later.